In this video, we're going to go through some steps of how to choose the proper buffer. So in the case of a weak acid and its salt, the buffer capacity definitely depends on the concentration of A- over HA. Because remember from the Henderson-Hasselbalch equation, the pH is going to be equal to the pKa plus the log of A- over HA. So if we look at these two concentrations of A- over HA, the buffer has its maximum capacity when these values are large and equal. So when the concentration of A- is equal to the concentration of HA, the pH equals the pKa. If the desired pH is equal to 4, you would choose a buffer with a pKa close to 4. So let's look at a particular example. A chemist needs a solution buffered at a pH equal to 4.30. Which of the following acids would they choose? Okay, so we're going to look at chloroacetic acid, propanoic acid, benzoic acid, and hypochlorous acid. And in order to do a proper analysis, we need the Ka values. So we can look those up. And the first one will be 1.35 times 10 to the minus 3. The second is 1.3 times 10 to the minus 5. Third, 6.4 times 10 to the minus 5. And the last one, 3.5 times 10 to the minus 8. First thing we need to look at is the pKa. So let's take each of these Ka values, do the negative log, and we'll calculate the pKa. Here we'll have 2.87, 4.89, 4.20, and 7.5 for our values. So in terms of the best choice, our best choice is going to be the acid with the pKa equal to 4.20 because this value is closest to what we're looking for with the pH, which is 4.30. So benzoic acid is the best choice. So now the question is, how would we prepare a buffer solution? Okay, we're going to remember that the pH is equal to the pKa plus the log of the concentration of A-, which will be C6H5COO-, divided by the concentration of C6H5COOH. Okay, so in this particular example, our pH is 4.30. That's going to equal the pKa, which is 4.20, plus the log of the concentration of C6 H5COO minus divided by the concentration of C6H5COOH. Our difference between the pH and the pKa is going to be 0.10 is going to equal the log of the concentration of C6H5COO minus divided by the concentration of C6H5COOH. If we do the algebra here, this is going to give us 1.25 is going to be equal to the concentration of C6H5COO minus divided by the concentration of C6H5COOH. So in this case, the ratio of C6H5COO minus to C6H5COOH must be greater than 1.25. Okay, so in this case we're going to prepare this buffer solution, and we need more salt added in that particular solution. So and we can really prepare these in any type of ratio, but remember, we want these values right here to be fairly large. So we're not going to prepare a really small concentration, but the ratio of the acetate ion has to be 1.25 times greater, the ratio here of our C6H5COO minus ion has to be 1.25 times the concentration of our benzoic acid. Okay, so in choosing the proper buffer, okay, we want our concentrations to be large and equal, and our pH needs to be as close as it can be to the pKa. So if we're given a particular pH, we want to choose the pKa that's the closest to it. In this case, if we're choosing a buffer with a pH of 4.3, we would want to choose benzoic acid based on the list of acids that we were given. Then we can use the Henderson-Hasselbalch equation to determine the proper ratio of A minus to HA that we will need, and in this case we found that more salt needs to be added to make the best buffer solution.